Electricity, so deeply embedded in the fabric of modern civilization, we are seldom even really aware that we're using it constantly. For illumination, heating, cooling our homes, preserving and cooking food, heating water, keeping time, washing clothes and dishes, entertaining ourselves, communicating, computing, printing, drying our hair, lifting garage doors, vacuuming, ironing. You get the idea. Your car needs electricity to run even if it's powered by gasoline. Electricity is also essential for the other infrastructure systems covered in this course: telecommunications, transportation, water and wastewater treatment, oil and natural gas extraction, mining, and solid waste disposal. Even electric power generation requires electricity. Electric power lines are such an integral part of our landscape that we scarcely notice them. And in a larger sense, our quality of life, our economic prosperity, our institutions, and even our interpersonal relationships depend to a surprising degree on that invisible source of energy instantly acquired by flipping a switch or inserting a plug. And so it should come as no surprise that collectively we use an incomprehensibly large quantity of electrical power. US power companies alone generate over 10 billion kilowatt hours of electricity per day. That's a big number, but what does it really mean? Well, before I can even attempt to answer that question, we need to review some key concepts from the science of thermodynamics that will be vital to our understanding, not just of this one statistic, but of this and all of our future energy-related lectures as well. Now, there are many forms of energy. We've already worked with two of them: gravitational potential energy, the energy associated with the elevation of a mass, and kinetic energy, the energy of motion. Others that are relevant to this course include electrical energy, another form of potential energy associated with a difference in voltage rather than a difference in elevation; internal energy, associated with the microscopic motions of the particles that constitute matter; elastic energy, associated with the deformation of a material; chemical energy, associated with the bonds between the atoms that constitute molecules; nuclear energy, associated with the bonds between the particles that constitute the atomic nucleus; and radiant energy, associated with light and other forms of electromagnetic radiation. There are also two principal forms of energy transfer: heat and work. Heat is the thermal energy transferred from a region of higher temperature to a region of lower temperature, and work is the energy transferred through the movement of a force through a distance. Of all forms of energy, work is perhaps the easiest one to visualize, so let's look at it more closely. Work is defined mathematically as force times distance, typically expressed as foot-pounds in the US system of units and Newton meters in the international system. 1 Newton meter is called a joule. Now, this small apple weighs about 1 Newton. And if I lift this apple vertically 1 meter, like this, I'm applying a force of 1 Newton through a distance of 1 meter. So I'm doing 1 joule of work. Now, work is a form of energy transfer. So when I do work on this apple, I transfer energy to it. In this case, increasing its potential energy by 1 joule. Now, if the apple falls 1 meter, its potential energy is converted into 1 joule of kinetic energy at the point just before I caught it with my lower hand. And here we can see what makes this concept of energy so powerful. At the most fundamental level, all of these different forms of energy are the same thing. As the law of conservation of energy tells us, energy can never be created or destroyed, but it can be transformed from one form into another. Thus, in a coal-fired power plant, we'll see a succession of transformations from the chemical energy in coal to internal energy in steam to the kinetic energy of a spinning turbine to electrical energy. In a hydroelectric generating facility, we'll see the potential energy of water in a reservoir transformed into the kinetic energy of a turbine and then again into electrical energy. And in photovoltaics or solar panels, we'll see the radiant energy of light transformed directly into electrical energy. As you can see, these transformations are vital because they allow us to use energy from a given source in ways that wouldn't otherwise be possible. I can use natural gas to heat my home, but I can't use it to power my computer unless I first transform its chemical energy into the electrical energy my computer is expecting. In a sense, our ability to engineer these transformations has made it possible for us to use electrical power as a sort of common currency for our energy-intensive world. By the way, power is formally defined as the rate at which work is done, or the rate at which energy is transferred. Thus, in US units, power is expressed in foot-pounds per second, or more commonly in horsepower, where 1 horsepower equals 550 foot-pounds per second. In the international system, the standard unit of power is the watt, which we also use quite commonly in the US. A watt is defined as 1 Newton meter per second, or 1 joule per second. Thus, if it takes me 1 second to lift my 1 Newton apple a distance of 1 meter, then the rate at which I'm doing work is 1 watt. Now, if I keep doing this for 1 hour, that's 3,600 lifts at 1 second each, I will have expended 1 watt-hour of energy. And after 1,000 hours, or 3,600,000 lifts, I will have expended 1 kilowatt-hour. And that, finally, brings us back to the US electrical power output of 10 billion kilowatt-hours per day. To expend this same amount of energy produced by US power companies in a single day, I would need to lift my apple at a rate of 1 meter per second for just over 1 billion years. Needless to say, I won't be demonstrating this in today's lecture. The principal reason why electricity has become the common currency of our energy-intensive world is that every significant natural source of energy available to us can be used to generate electrical power. As of 2013, about 2/3 of electrical power in the US was generated by burning fossil fuels, mostly coal, just a bit of oil, and a growing amount of natural gas. About 20% was from nuclear fission, and 13% from renewable sources, which include hydroelectric, wind, solar, and geothermal, and biomass, though the use of renewables is growing rapidly as well. Worldwide, the average percentages are similar, but there's significant variation from country to country based on resource availability and political decision-making. For the remainder of today's lecture, we'll focus on the dominant source of electricity in the US, over 500 coal-fired power plants with total generating capacity of over 300 billion watts. Now, there are reasons why we get more of our power from this stuff than from any other source. Coal is the most abundant fossil fuel in the Earth's crust. It's relatively inexpensive, and in contrast with oil, ample supplies are available in politically stable regions of the world. Coal can be transported efficiently by rail, and as we'll see, our freight rail system serves this purpose quite well. Moreover, as a source of energy, coal is unsuitable for use in vehicles and, in recent decades, has fallen out of favor as a source of heat for residential and commercial buildings. Thus, if we're going to tap this abundant source of energy on a large scale, generating power is practically the only way to do it. Of course, burning coal is also highly problematic because of its contributions to both air pollution and carbon emissions, challenges we'll discuss later in this lecture. But first, let's look more closely at how a coal-fired power plant works as a technological system. From a macro perspective, This system consists of three self-contained but closely interwoven subsystems. One for burning coal to produce a stream of hot flue gas. One for extracting heat from the flue gas to produce a continuous stream of high-pressure steam that drives a turbine. And one for transforming the turbine's shaft power into electrical power. As I explain the power generation process in detail, keep these three major subsystems in mind and note how closely and intricately they're interconnected. Also, recall that from an engineering perspective, the term fluid refers to either a liquid or a gas. This is important because in the steam power generation cycle that we're about to examine, the working fluid is water, which is converted from liquid to gas and back to liquid as it moves through the cycle. Now, power generation begins with the delivery of massive amounts of coal to the plant by railroad or barge. It's common to see long chains of hopper cars like these lined up outside a power plant waiting to be unloaded. And by the way, the hopper car is so named because it can be unloaded quite efficiently by opening these chutes on its underside. A large generating plant consumes about 250 tons of coal per hour, so efficient handling is essential. And that's why another distinguishing characteristic of these facilities is this large conveyor belt, providing a continuous flow of coal from the storage yard into the plant. Inside, the coal enters a pulverizer, a rotating drum containing large steel balls that grind lumps of coal into a fine powder, which is then blown into the furnace with high-powered fans. Powdered coal burns more completely than larger pieces do. Thus, pulverizing increases fuel efficiency while also reducing pollution. The furnace is a huge steel box, about 50 feet square and 130 feet tall. Inside, a 3,000-degree fireball burns continuously, sending a stream of hot exhaust gases up into this arch-shaped flue. As we'll see, the purpose of the flue and its associated equipment is to extract every possible joule of heat from the exhaust gases before they're released into the atmosphere. The process of heat transfer begins with the boiler, consisting of tightly packed vertical steel tubes called risers, which are actually integrated within the walls of the furnace itself. The risers are filled with water that boils and rises as it's heated by radiant energy from the flames. Each riser is actually part of a closed loop that allows for continuous circulation of this fluid. At the top of the loop is a device called a steam drum, which separates steam from the water. Tapping steam from a vessel of boiling water might seem like a straightforward process, but when the vessel is fully enclosed and pressurized to about 2,600 pounds per square inch, it takes a centrifuge spinning inside the steam drum to segregate the light steam from the heavy water. The separated steam is now piped to the next stage of the power generation process. It's part of a larger closed loop that constitutes the steam power generation cycle, often called the Rankine cycle in the science of thermodynamics. We'll return to this cycle momentarily. Meanwhile, the separated water is circulated from the steam drum back down to the bottom of the furnace through pipes called downcomers. And then it's fed back into the risers where the generation of steam continues. This massive assembly of risers, downcomers, and steam drums isn't supported on the floor of the plant. It actually hangs from a structure overhead to allow for the thermal expansion and contraction of the pipes through their huge range of operating temperatures. Now, according to the laws of thermodynamics, the efficiency of a steam power cycle can be improved by increasing the temperature of the steam that's fed into the turbine. And that's why the high-pressure steam emerging from the steam drum is now routed through this superheater, suspended within the hottest part of the arch-shaped flue. The superheater is really just a heat exchanger. Intensely hot flue gases flow across its coils, raising the temperature of the steam to about 1,000 degrees Fahrenheit, at which point it's ready for the turbine. A steam turbine is a mechanical device that converts the internal energy in steam into the kinetic energy of a rotating shaft. All we can actually see in this photo is the heavy airtight casing, which is required to withstand the immense internal pressure the turbine experiences during use. If we could look inside, we'd see this: a series of discs rigidly fixed to a shaft. Each disc is called a rotor and is composed of closely spaced angled blades. Alternating between the rotors, another set of similar discs, called stators, is rigidly fixed to the inside of the casing. The rotors turn with the turbine shaft, the stators stand still. Each pairing of one stator and one rotor is called a stage of the turbine. And here's how it works. High pressure steam enters at the narrow end of the turbine and it moves toward the wider end, passing through successively larger stages and expanding as it goes. The blades of each stator are configured such that the flow of steam through them is constricted. And just like wind blowing over the roof of a house, when the steam flows through this constricted space between the blades, it speeds up. As high velocity steam emerges from the stator, it passes through the angled blades of the rotor, which deflect the steam as you see here. As the steam changes direction, it applies a force to the blades, and like a windmill, the force turns the rotor. The steam, now with a little bit less internal energy, passes to the next stage, where it's accelerated by the second stator before imparting energy to the associated rotor. Because the steam expands through each stage, the rotors need to be progressively larger to capture the steam's energy as efficiently as possible. And so the process continues, stage by stage, until the steam is exhausted at considerably lower pressure from the far end of the turbine. But the process of converting the internal energy of steam into kinetic energy is far from over. Most power plants actually have 3 turbines driving the same shaft. The first is a high-pressure turbine that receives its steam directly from the superheater and then sends it back to a reheater located just beyond the superheater in the flue. The reheater transfers more waste heat from the flue gases into the steam, raising its temperature close to 1,000 degrees Fahrenheit, though not increasing its pressure appreciably. And now the steam is piped in succession to an intermediate pressure turbine and a low pressure turbine, which extract even more energy and transmit it to the rotating shaft. These 2 turbines must be physically larger than the high pressure turbine because lower pressure steam occupies more volume. But together, these 2 larger machines actually account for only about 40% of the kinetic energy imparted to the shaft. The smaller high-pressure turbine actually does most of the heavy lifting. Before we move on from the turbines, we should pause to marvel at these extraordinary machines. The rotor blades, precisely machined from a specialized steel alloy, must withstand incredibly high temperature, pressure, mechanical stress, and the corrosive effect of constant exposure to moisture, all while spinning in perfect balance at a carefully controlled rate of 60 revolutions per second, for reasons we'll discuss in a future lecture. And they're beautiful too. Steam leaving the low-pressure turbine now enters a condenser, which changes the vapor back into liquid water for eventual return to the boiler. As the steam condenses, its pressure decreases considerably, creating a partial vacuum that actually helps pull the waste steam out of the turbine. Note that the movement of steam through this closed system is a continuous flow from steam drum to superheater to high-pressure turbine to reheater to intermediate and low-pressure turbines to condenser. Although the steam's temperature and pressure change substantially during this trip, the number of water molecules per second departing from the steam drum is identical to the number entering the condenser, allowing, of course, for small losses due to leaks. Water collected from the bottom of the condenser will eventually be recirculated to the boiler to complete the so-called feed water loop. But before this can happen, the feed water is intensively purified to remove rust particles, dissolved minerals, dissolved oxygen, and acidity, all of which can foul the riser pipes or promote deterioration of those critically important turbine blades. The purified water is then pumped through a device called an economizer here, which extracts even more waste heat from the flue gases, and then back into the steam drum, where it rejoins the flow of water through the downcomers to the boiler. But the job of extracting energy from those flue gases still isn't done. A heat exchanger at the end of the flue here is used to preheat the stream of fresh air that's mixed with pulverized coal and blown into the boiler at the very start of this process. Finally, these exhaust gases are processed through a series of pollution control devices and then released through the top of a smokestack into the atmosphere. Meanwhile, back in the powerhouse, the ultimate purpose of all these interwoven processes is finally realized. The turbine shaft turns the generator, which generates electrical power. Now, before I explain how a generator works, we need to review two key electrical concepts: current and voltage. Current is the flow of electrons through a conductor, like this copper wire, when it's subjected to a voltage, defined as a difference in electrical potential energy between 2 points. On this battery, there's a 6-volt difference in electrical potential energy between the two battery terminals. But that potential will only cause a current if I connect the two terminals with a conductor. And the result is called a circuit. As you can see, when I make that connection, the current flowing through this circuit is sufficient to light this light bulb. And because the voltage supplied by the battery is at a steady 6 volts, the resulting current is also unvarying. And so we see a steady glow from the bulb. We call this direct current, or DC. Now, the generator. All electrical power generation is based on the principle of electromagnetic induction, discovered independently by Michael Faraday and Joseph Henry around 1830. This principle states that an electric voltage will be developed in a conductor that's exposed to a varying magnetic field. Let's see this principle in action with a simple homemade generator. Here I've wound copper wire into a coil around the framework of my homemade device. Inside of that framework is a magnet mounted on a rotating shaft. Now, interestingly, generators use the same terminology as turbines. The rotating magnet is called the rotor, and the stationary coil is called the stator. When I spin the rotor, the stator will be exposed to a varying magnetic field, which will generate a voltage. Now, my little homemade generator isn't terribly efficient, and it definitely won't generate the 6 volts I would need to light this incandescent light bulb. So instead, I've connected it to a highly energy efficient, low voltage, light emitting diode, or LED instead. Ready, I'll now spin the generator. Let's see how it works. If you watch very carefully, you'll see that as I spin the rotor, the bulb flickers as I turn it. This happens because both the voltage and current in the coil vary with the continuously varying intensity of the rotating magnetic field. Thus, in contrast with the direct current supplied by my battery, this generator is producing alternating current, or AC. The periodic variation of alternating current can be represented mathematically as a sine curve, shown here, with each rotation of the shaft producing one full cycle of both voltage and current. Electrical power produced in this manner is called AC power. The full-scale generator in a power plant works in essentially the same way as my model, with just 3 important exceptions. First, obviously, the full-scale generator is driven not by hand, but by 3 steam turbines, and it generates hundreds of megawatts of AC power. Second, in a full-scale generator, the stator has 3 separate coils, equally spaced around its circumference. Thus, one turn of the rotor produces 3 separate voltages, one in each coil. The result is 3-phase power, a concept so important that I'll reserve it for a more detailed discussion in our lecture on electrical power transmission. And third, to achieve the strong, controllable magnetic field required for a power plant generator, a permanent magnet like the one in my model just won't cut it. The rotor must be an electromagnet. Now, the electromagnet is an application of another important law of physics, which says that an electric current flowing through a conductor produces a magnetic field. Here, I've wrapped my copper wire around a large nail. And when I now connect the ends of the wire to a battery, current flowing through that coil creates a magnetic field, which allows me to pick up these paper clips. Now let's pause a second and note the fundamental difference between this phenomenon and the principle of electromagnetic induction, which we just observed in our generator. Electromagnetic induction requires a varying magnetic field to produce a current. But any current, varying or constant, will produce a magnetic field. And that's why my electromagnet works just fine with the direct current produced by this battery. A generator's output voltage can be controlled by varying the strength of the magnetic field produced by the rotor. And the strength of an electromagnet's field can be controlled by varying the current flowing through the electromagnet. Thus, the great advantage of using an electromagnet in the rotor of a power plant generator is that it provides a mechanism for controlling the generator's output voltage. But wait, if the electromagnet requires an electric current to produce its magnetic field, where does this electricity come from? Well, the answer is another generator. This one, a significantly smaller generator called the exciter, is driven by the same shaft as the main generator, but its rotor uses permanent magnets, like the one in my model, and thus doesn't rely on an external source of electrical power. Meanwhile, back at the power plant, the electricity produced by the main generator is transmitted to this adjacent switch yard, where a small portion is diverted back into the plant to drive pumps, conveyors, lighting, and such. The remainder begins a long journey that will eventually culminate in your home, a journey that we too shall take in our later lectures on power transmission and distribution. The coal-fired power plant is a beautifully engineered infrastructure system that has served us well for over a century. Yet this system faces an uncertain future because of its adverse effects on our environment. These effects are intrinsic to the chemistry of combustion, which lies at the heart of all fossil fuel burning technologies. The principal chemical reaction associated with burning coal is quite simple. Carbon from the coal combines with oxygen in the air to form carbon dioxide and energy. The U.S. Environmental Protection Agency tells us that CO2 accounts for 82% of all greenhouse gas emissions and thus is a major contributor to climate change, and that 1/3 of man-made CO2 emissions result from the combustion of fossil fuels in power generation. The fundamental challenge is that the production of CO2 is integral to the chemical process of combustion. We simply can't acquire energies from fossil fuels without producing CO2. And carbon emission isn't the only challenge. Each lump of coal includes some mineral content that just won't burn and becomes a fine gray ash during combustion. If this stuff isn't removed from the furnace exhaust stream, it becomes air pollution. Most coal also contains some sulfur, and during combustion, this impurity reacts with oxygen to form sulfur dioxide. Similarly, at the extreme temperature of coal combustion, some nitrogen in the air is also oxidized to create various nitrogen oxides, abbreviated NOx or NOx. Both sulfur dioxide and NOx are chemical precursors of acid rain. These challenges are daunting, but they're not insurmountable. The past few decades have seen the development of highly effective clean coal technologies. The electrostatic precipitator to remove ash, the scrubber to remove sulfur dioxide, selective catalytic reduction for NOx. The challenge of carbon emission remains, yet even here, a series of new technologies for carbon sequestration hold great promise for preserving the viability of power generation from fossil fuels. In carbon sequestration, CO2 is captured from the furnace exhaust and either stored in deep geologic formations underground or reacted chemically with metal oxides to produce stable, solid materials called carbonates. But even as carbon sequestration technology is being refined and tested, power companies are shutting down many older, less efficient coal-fired plants in anticipation of stricter federal emission standards. In 2012 alone, coal-based generating capacity totaling over 10,000 megawatts was retired, and that number is expected to increase sharply over the next few years. Nonetheless, the impracticality of replacing all our coal-based generating capacity in the short term and the real possibility of a technological solution to the carbon emission challenge suggests that coal will be part of our energy portfolio for many years to come. In the next lecture, we'll see how the technologies used for generating electric power from oil, natural gas, and nuclear fission are really just adaptations of the process we learned about here. Yet another reason why coal-fired power generation is something worth knowing about. In 2007, US generation of electric power from coal peaked at just over 2 trillion kilowatt hours per year. By 2013, that number had dropped by over 20% to 1.6 trillion kilowatt hours. Now, as we learned last lecture, a major factor in this decline has been the tightening of federal standards for air quality and carbon emissions, and the promise of more to come. Meeting these standards requires the installation of expensive pollution control equipment like scrubbers and electrostatic precipitators, which can cost hundreds of millions of dollars per unit. For many older, less efficient plants, these modifications are either infeasible or just too expensive, and shutting them down is proving to be the only economically feasible course of action for many power companies. During the same period, over 50 proposed new coal-fired power plants have been canceled or placed on hold. But the decline in coal-fired power production isn't solely a product of government regulation. It has also been facilitated by other dramatic developments in the energy industry. To understand these developments, let's start by looking more broadly at trends in power generation over the past 6 decades. During this period, as US demand for electrical power has climbed inexorably upward, every source of electrical power has seen a distinctly different historical trend. We've already seen the trend for coal, a steady climb followed by a precipitous decline starting in about 2009. Hydroelectric power generation grew gradually until the early 1970s, when environmental concerns dampened enthusiasm for the construction of new dams. Power from the combustion of oil grew sharply in the 1960s and 70s, but then declined sharply when oil prices skyrocketed in the aftermath of the Arab oil embargo of 1973 and 74. Nuclear power climbed aggressively after it became commercially viable in the late 1960s, and then it faltered after the 3 Mile Island power plant accident in 1979. Subsequent growth can be attributed primarily to the completion of nuclear plants that were already under construction in 1979. Renewable sources other than hydropower weren't even significant enough to track until 1988, but in the past decade, they've seen impressive growth, driven by both government policies and popular support. Finally, the most dramatic trend in US power generation is that of natural gas, which had been on a gradual decline from 1970 through the late 1980s, but has surged upward at an ever-increasing rate since then. This ongoing boom in power generation from natural gas is the product of hydraulic fracturing, or fracking, the highly effective and highly controversial process that's now being used to extract previously unrecoverable natural gas and oil deposits from shale, as we discussed a few lectures ago. In this lecture, we'll see the 2 principal effects of fracking: a significant increase in our domestic natural gas supply and a significant reduction in its cost. By 2012, the price of natural gas had fallen to 30% of its peak in 2005. It's clear then that abundant, low cost natural gas has accelerated the shutdown of coal fired power plants by providing an economically viable substitute for the capacity lost to shutdowns. And what broader conclusions might we draw from this rather dramatic picture of trends in power production? Note that if we extrapolate recent trends, we might conclude that coal will be phased out entirely within 10 years, with the lost capacity being replaced by continued dramatic growth in natural gas and renewables. But in fact, the U.S. Energy Information Administration, the federal agency charged with doing these sorts of projections, paints a very different picture. According to the EIA, natural gas prices will soon start rising again as producers do more drilling in areas where the recovery of gas is more difficult. These price increases will moderate the growth of gas-fired power production while facilitating a modest rebound in coal. Thus, natural gas won't actually surpass coal as an energy source until around 2035. So perhaps the most important lesson we should learn from this graph is that trends in energy production are often both unpredictable and volatile, with drastic changes triggered by international conflicts, domestic political decisions, technological developments, technological failures, and changing societal values. Given this unpredictability, the diversity of our energy portfolio is one of its greatest strengths. And that's why in this lecture, we'll be examining the three conventional power generation alternatives to coal: oil, natural gas, and nuclear fission. And then in the next lecture, the three most important sources of renewable energy: hydroelectric, wind, and solar. Now, I don't need to spend a lot of time talking about power generation from oil, in part because this source accounts for less than 1% of US electrical power, but also because the associated technology is so similar to the coal-fueled plants that we examined last lecture. Indeed, the only significant difference is that the coal furnace is now replaced by an oil furnace, fueled by oil sprayed into the combustion chamber through a series of nozzles. The nozzles break up the stream of oil into tiny droplets for more complete combustion, just as pulverized coal is used to achieve better combustion in coal furnaces. Beyond the furnace, the operation of an oil-fired plant is essentially identical to that of a coal-fired plant. Heat from the furnace boils water, which is used to drive steam turbines, which drive generators to produce power. And burning oil carries with it the same major disadvantages: air pollution and carbon emissions, the inevitable byproducts of the chemistry of combustion. Now, an interesting benefit of oil-fired power generation is its use of a fuel that serves no other practical purpose: the thick, corrosive bottom product of the petroleum refining process. Suffice it to say that this petrochemical sludge is a far cry from the light fuel oils used for home heating. It's so thick that it must be heated to over 100 degrees Fahrenheit just to move it through a pipeline. As such, even though oil is likely to continue making only a minor contribution to US power production, it will remain a useful means of disposing of an otherwise useless waste product. Next, we'll look more closely at natural gas, which currently fuels about 28% of US power generation. The operation of a gas-fired power plant is fundamentally different from that of a coal or oil-fired plant, in that it does not use the combustion of fossil fuel to boil water. Rather, it uses a fundamentally different type of turbine called a combustion turbine that's driven directly by the combustion of natural gas. Power company employees sometimes refer to these gas turbines as jets, and the name's appropriate because the technology is a direct adaptation of the engines used to power jet aircraft, not to mention ships, trains, and even some military tanks. Here's a typical gas-fired power plant with 4 combustion turbines, and here's how the system works. The turbine is composed of 4 major components: a compressor, a combustion system, a turbine, and a drive shaft. The compressor, rotated at high velocity by the spinning shaft, draws air through this intake, compresses it, and feeds it into a ring of combustion chambers. Fuel injectors introduce a steady stream of natural gas into the chambers, and the resulting mixture of gas and compressed air is burned at a temperature of over 2,000 degrees Fahrenheit and then fed into the turbine. The hot, high-pressure exhaust gas expands through the turbine in essentially the same way that steam expands through a steam turbine, spinning the rotors, which drive the shaft that powers both the compressor and the generator. The generator sends three-phase power to the adjacent switch yard, just like a coal-fired plant. Now, the thermodynamic efficiency of a combustion turbine is somewhat less than that of a steam turbine. However, the efficiency of the power generation system can be improved significantly by adding a piece of equipment called a heat recovery steam generator, which captures waste heat from the turbine exhaust and uses it to produce steam that drives a conventional steam turbine. The configuration is called a combined cycle plant. Now, natural gas has three significant advantages over coal as a fuel for power generation. First and foremost, the combustion of gas is significantly cleaner than the combustion of coal. In a recent study that directly measured emissions from exhaust stacks, gas-fired power plants emitted only 0.2% of the sulfur dioxide, 7% of the NOx, and 60% of the CO2 emitted by coal-fired plants. Emission per kilowatt hour were even lower for combined cycle plants. Second, a natural gas-fired plant has a much smaller physical footprint than a coal-fired plant with the same power output. For this reason, gas-fired plants have been particularly popular in urban areas with limited space. And third, a combustion turbine can be started up and shut down easily and quickly, while starting up a coal furnace takes the better part of a day. As a result, coal-fired plants are designed to run 24 hours per day and to shut down only for maintenance. As we'll learn in our lecture on power transmission, one of the greatest challenges in managing power production is that at any given moment, the amount of power generated must exactly match the demand. These graphs show how consumer demand for power varies over the course of a typical day in summer and in winter. The lower region of each graph, called the base load, can be met quite efficiently by coal-fired power plants running 24 hours a day because it doesn't change. But the peak loads are much better met by gas-fired plants, which can be started up and shut down on short notice as the situation dictates. Even before the current boom in natural gas production, power companies often installed a few supplemental combustion turbines at large coal-fired power plants just for this purpose. Now, given these substantial advantages, natural gas is the answer to all of our energy challenges, right? Well, no. Even though gas is much cleaner than coal, burning natural gas still emits pollutants and relatively large amounts of CO2. In this sense, nuclear, hydroelectric, wind, solar, and geothermal power generation are all superior because they produce no emissions at all. Combustion turbines are also extremely loud. After all, they are jet engines. And most importantly, there are serious environmental concerns about fracking, the technology underlying the ongoing natural gas production boom. As we'll see again and again throughout these lectures, there is no perfect energy source. And that brings us to nuclear power, the source of roughly 20% of the electrical power used in the US and 13% worldwide. With 99 reactors at 61 nuclear power plants nationwide, the US is currently the world's largest supplier of commercial nuclear power in terms of raw output. A nuclear power plant is similar to a coal-fired plant in the sense that both use closed-loop steam cycles to spin turbines. The big difference is simply that the source of energy used to produce the steam is different. It's chemical energy for a coal-fired plant, nuclear fission for a nuclear plant. Nuclear fission, the splitting of atomic nuclei, depends on the unique behavior of certain heavy elements called fissile materials, which are used as nuclear fuel. By the way, the word fissile means easily split. And so a fissile material is one that's capable of sustaining the chain reaction associated with nuclear fission. The most common fissile material is uranium-235. When the nucleus of a U-235 atom is struck by a neutron, it breaks apart, releases energy, and emits a few free neutrons. If a sufficient quantity of this material is assembled in one place, the neutrons emitted by the fission of one nucleus will encounter adjacent nuclei, causing them to split, release energy, and emit more neutrons. As this process continues, progressively more free neutrons cause the fission of progressively more nuclei, and the result is a nuclear chain reaction, self-sustaining fission. If this chain reaction is controlled, we have a very potent source of energy. If it's uncontrolled, we have a nuclear explosion. But how does this reaction get started in the first place? Well, uranium-235 experiences a small amount of spontaneous fission, a natural form of radioactive decay that releases a few neutrons. So we really only need to assemble a critical mass of uranium-235, and this natural emission of neutrons will set the nuclear chain reaction in motion. Nuclear fuel is prepared for use in a reactor by molding uranium into small pellets, which are then sealed inside metal tubes to create fuel rods. The tubes are made of zirconium alloy, used because of its corrosion resistance and low neutron absorption. The purpose of the tube is to contain the uranium pellets so fragments can't break away and contaminate the reactor coolant. The fuel rods are assembled into bundles of about 200 each, like this, and about 150 such bundles are then combined to form the reactor core. These holes in each bundle allow for the insertion of control rods, cylindrical bars made of boron carbide, a material that's particularly effective at absorbing neutrons. When the control rods are inserted into a fuel bundle, they absorb enough free neutrons to prevent the fission reaction from sustaining itself. Thus, they keep the nuclear reaction from getting out of control. When they're withdrawn, they allow the reaction to proceed. Now, there are two different types of reactors used in most U.S. nuclear power plants. The more common is the pressurized water reactor, or PWR. In a PWR, reactor core is kept fully immersed in coolant water within the reactor vessel, a 40-foot tall cylindrical capsule with 9-inch thick steel walls. The water is kept at such high pressure that it can't boil, even though it's heated to 600 degrees Fahrenheit. This pressurized water is pumped from the reactor vessel through a steam generator and then back to the reactor. The circuit is called the primary loop. Within the steam generator, which is really just a heat exchanger, heat from the primary loop is transferred into a separate reservoir of water. And the resulting steam is then routed through the secondary loop to a steam turbine, which drives an electrical generator. The steam is then condensed back to liquid and recirculated to the steam generator. An important safety feature of the PWR is that the secondary loop, which drives the turbine, is kept completely segregated from the primary loop, which circulates coolant through the reactor. Thus, reactor coolant never enters the secondary loop, and water from the secondary loop never enters the reactor vessel, so that chances of radioactive contamination are minimized. In a PWR, the control rods are mounted on the top of the reactor vessel, as you see here. To initiate the nuclear reaction, then, the control rods are just lifted hydraulically. To slow or stop it, they're lowered. And in the event of a power failure, the rods simply fall back into the core to stop the reaction, an important safety feature. For added safety, the reactor vessel, the steam generator, and the pumps used to pressurize the primary loop are all situated within this massive domed concrete containment building. We can tell that the Diablo Canyon power plant in California has 2 PWR reactors because it has these 2 containment buildings. Adjacent to the containment buildings is the fuel handling facility, which is used to support the refueling of the reactor every year or two. Refueling is a complex operation in which the top of the reactor vessel is lifted off with a crane, spent fuel rods are removed, and then transported through a flooded tunnel to a deep pool of water in the fuel handling facility, and then new fuel rods are transported back through that same tunnel and installed in the reactor. The second type of reactor used in about 1/3 of U.S. nuclear plants is the boiling water reactor, or BWR. The BWR differs from the PWR in that the coolant water is allowed to boil by keeping the reactor vessel at a lower pressure. The resulting steam is piped from the top of the vessel directly to the turbine and then condensed and recirculated back to the reactor. Thus, the BWR process uses only one loop rather than two, and the entire loop, including the reactor, turbines, generator, and condenser, is typically contained within a single large building, as you can see at the Browns Ferry nuclear plant in Alabama. Note that there are no domed containment buildings at a BWR facility. The BWR configuration has the advantage of simplicity. However, in comparison with the PWR, it also has two significant disadvantages. First, because the outgoing steam lines are necessarily connected to the top of the reactor vessel, the control rods must now be inserted from below. In this configuration, gravity won't work as an emergency shutdown mechanism, so an elaborate hydraulically operated shutdown system is required. More importantly, the single-loop configuration inevitably causes low-level radioactive contamination of the circulating steam. And some water molecules are actually broken apart into radioactive forms of hydrogen and oxygen. A separate system is required to capture these gases from the condenser and dispose of them. And that's why another distinguishing characteristic of the BWR facility is this extremely tall stack, as you can see at Browns Ferry. The stack is used to disperse those radioactive gases as high into the atmosphere as possible. The level of radioactivity in these emissions is extremely low, far below the stringent standards set by the Nuclear Regulatory Commission. Nonetheless, it is worth noting that radioactive emissions are an integral part of the BWR process. Now, speaking of distinguishing characteristics, how about this one? The hyperboloid cooling tower. So named because its shape is based on a mathematical hyperbola. Probably because of its association with the 3 Mile Island facility as shown here, the cooling tower has become an iconic and distinctly negative symbol of nuclear power. This symbolic association is both flawed and unfortunate for several reasons. First, not all nuclear plants use hyperboloid cooling towers, and many other types of power plants do use them. Note that this coal-fired plant in Pennsylvania has 2 of them, while the Diablo Canyon nuclear facility has none. The most common type of cooling tower used at all types of power plants, nuclear and otherwise, is this low rectangular structure at Browns Ferry. And here's how it works. In order to cool and condense the steam exhausted from the turbines, a self-contained loop of cooling water is circulated through the condenser. As it removes heat from the steam, this water gets hot and must itself be cooled off before it can be recirculated or returned to the watercourse from which it came. And this is necessary because dumping hot water into a river can harm aquatic life. The hot water is pumped to the top of the cooling tower, distributed around its perimeter, and then allowed to trickle down through an open web of plastic called fill. At the same time, huge fans mounted at the top of the tower draw fresh air inward through louvers in the walls, through the fill, and then out through the roof. The moving air evaporates some of the water trickling down through the fill, and evaporation cools the remaining water back to its normal temperature by the time it reaches this basin at the bottom of the tower. Some of this cooled water is discharged back into the river to prevent the concentration of dissolved minerals from getting too high. Fresh water from the river is then added to replace the losses from both discharge and evaporation, and then the cooled water is recirculated back to the condenser. Because this cooling water never intermingles with the water and steam that drives the turbines, there's no chance of contamination here. The hyperboloid cooling tower works in exactly the same way, except it has no fan. The shape of the tower draws the warm air inside upward, and this natural draft pulls air in through the open framework at the base. As a result, the same cooling effect can be obtained without the expenditure of the huge amount of electrical power required by those fans in a conventional cooling tower. So, this ominous symbol of nuclear power is actually an energy-efficient device for protecting fish. And that nasty-looking plume billowing from the top, it's 100% water vapor. Now, it's important to recognize that from a macro perspective, the advantages of nuclear power are considerable. Nuclear plants can operate at max capacity for extended periods of time, so they're very effective at meeting base load. Although nuclear fuel is a non renewable resource, there's enough of it in the Earth's crust to last for centuries. More importantly, properly contained nuclear fission produces minimal air pollution and no CO2. In the first decade of the 21st century, a growing appreciation for these advantages, coupled with post 9/11 concerns about our dependence on energy sources from unstable regions of the world, led to a resurgence in enthusiasm for nuclear power, both in the US and abroad. Many new power plant construction projects were initiated, and there was talk of a nuclear renaissance and of nuclear power as a major component of a new environmentally friendly power generation system. Then came the 2011 Fukushima power plant disaster, throwing the nuclear industry back on its heels once again. The Fukushima incident was triggered by a magnitude 9.0 earthquake off the coast of Japan. Initially, the plant's safety systems worked exactly as they were supposed to. In all three operating reactors, control rods were inserted into the reactor cores to shut down self-sustained fission, and emergency generators were switched on to power the cooling systems. This is an essential aspect of nuclear safety because even after the control rods stop the self-sustaining fission reaction, the reactor core continues to produce tremendous heat for many hours because of continuing radioactive decay. Thus, it's critical to continue coolant circulation for several days after a shutdown. Tragically, at Fukushima, 50 minutes after the earthquake, an earthquake-induced tsunami overtopped the plant's protective seawall and flooded the facility, causing the emergency generators to fail. The plant's backup battery system immediately took over, but when the batteries went dead the following day, there was nothing to prevent all three reactor cores from melting down. In a meltdown, the nuclear fuel elements exceed their melting point, causing fission products to enter the coolant water and greatly increasing the possibility of a radioactive release from the containment vessel. At Fukushima, the result was a humanitarian, environmental, and economic catastrophe. Fukushima effectively ended the nuclear renaissance, while reminding the world that despite stringent regulations, exacting engineering codes, and extensive redundant backup systems, nuclear accidents can still happen. And when they do, the consequences can be dire indeed. Beyond the potential for nuclear accidents, the long-term viability of nuclear power is also plagued by the still unresolved challenge of nuclear waste disposal. This challenge is exacerbated by the high level of radioactivity in the products of nuclear fission. Several of the new elements created when uranium nuclei split apart have half-lives of over 1 million years. Given this long-lived hazard to life and health, the only feasible method of disposal is to completely isolate nuclear waste from the biosphere. There's a general scientific consensus that this sort of isolation would best be accomplished by building deep underground repositories in geologically stable areas. However, no such commercial facilities have yet been built, and as you might guess, nobody wants one in his backyard. In 2011, the federally funded Yucca Mountain Nuclear Waste Repository in Nevada was mothballed due to environmental and political opposition. In the meantime, highly radioactive spent nuclear fuel rods continue to accumulate at over 400 reactor sites around the world. These serious challenges notwithstanding, nuclear power is not going away anytime soon. In 2012, the U.S. Nuclear Regulatory Commission approved the construction of 4 new reactors at existing power plants. China, India, and South Korea are building new reactors as well. France currently generates 75% of its power with nuclear fission. And even in places where nuclear power has fallen out of favor, the immense capital investment in existing plants provides a strong incentive to keep them in operation for as long as possible. Over the past 4 decades, the history of nuclear power has been so troubled that it's easy to forget how differently the story began. Back in 1954, Louis Strauss, the chairman of the United States Atomic Energy Commission, predicted that harnessing the atom would make electricity so plentiful and so inexpensive that it would be too cheap to meter. And while we may scoff at Mr. Strauss's hubris today, it's not unusual to hear the same sorts of exuberant claims being made about new energy technologies today as well. We certainly shouldn't dismiss such claims, but we also shouldn't accept them without careful scrutiny from the social, political, economic, and technological perspectives. Speaking of exuberant claims, in the next lecture, we'll look at the brave new world of renewable energy, the principal technologies in use today, their advantages and disadvantages, and their prospects for the future.